an associate professor in the Department of Statistics at the University of Washington, Seattle. He got his PhD in statistics from Wisconsin-Madison in 2000. He's the winner of the 2000 Leonard Savage Award for Outstanding Doctoral Dissertation. And he has been working on latent space approaches to social network analysis, model-based subspace clustering, and constrained non-parametric maximum likelihood via measures.
All right, so thanks for having me out. It's been great to learn about the center here and all the things that go on. And I'm curious to see how some things I do might be useful for things that you might do, or how things that you do might push me along. So most of my examples today, well, I have several different examples. But as a statistician, I try to make my methodology very general and make it apply to lots of different types of situations. So for example, I'm going to use similar approaches to do data analysis for a biological network, a protein-protein interaction network, as well as a method for analyzing conflicts between countries. And so maybe along the way, somebody here can provide an example of interest to them. So please feel free to stop, ask me questions, and so on. Okay, so what I'm going to talk about today are what I call multiplicative factor models for relational data. And when I think of relational data, I'm thinking of measurements that are specific to, say, for example, pairs of objects. So in basic statistics, we think about measurements that are specific to a single object, right? So you have a bunch of objects and you have a bunch of measurements on these objects. In a lot of situations, you have data which are not specific to single objects, they're specific to pairs of objects. And I'm going to have some examples of that later on. So for example, I'm going to have data on conflicts between countries. So there are conflict, in some sense, is specific to a pair of countries. Interactions between proteins, specific to a pair of proteins. I'll have a data set on friendships among children, and so those are specific to pairs. Okay? So first I'm going to talk about some models for this type of data, and I'm going to have two different motivations for a latent factor model. And the resulting model uses ideas from matrix decomposition theory, which I think will be familiar to everybody. So it's kind of a simple, I think, straightforward, easy to understand approach to analyzing these data. And then, part two of the talk, I'm going to extend this to, so this first part of the talk is all on data on pairs, okay? And we're going to talk about a model for that. And then we're going to go on and extend this to data that are more general. There are data on triples, quadruples, and so on. And I'm going to talk about a very natural generalization of this stuff to these types of data. Okay, so in its simplest form, relational data consists of a set of units or nodes. So you have a node set A, and you have a set of measurements that are specific to pairs of nodes. Okay, so for every pair, you have potentially observed a measurement Yij for each pair of Ij in your node set. And so some examples of that. So you have international relations data, so maybe A is a set of countries, and Yij might be the indicator of a dispute between or initiated by country I and with target country J. So that's one example. So another example is a needle sharing network. So you have intravenous drug users. And so maybe Yij is the indicator of needle sharing activity between I and J. So notice here we have a direction to our relationship, and here we lack a direction. So this is just sharing needles. Protein-protein interaction data. So one type of experiment that's commonly done now is to see how proteins might bind to each other, and so some proteins do and some proteins don't, and so we might have data on interactions between pairs of proteins.
And that would be 0, 1, maybe?
Yeah, that would be 0, 1. It's often derived from data which are not 0, 1, but the belief is that the underlying process is 0 or 1. But maybe I'll get to that in more detail later. Okay, and actually, it turns out that some of these data, a lot of network data that I've seen before is actually derived from analysis of documents. Okay, and basically you have, you have a bunch of documents, information sources, you have words, and so for example, Yij might be the word count of word I in document J. Okay, so notice that this is a little bit different than the other situations where we have two different kinds of nodes. Okay, you can think about this data being put in a rectangular array where the row objects are different from the column objects. Okay, so those are the kinds of data that I'm thinking about when I talk about relational data. Okay? All right, so what does one hope to do with relational data? Well, there's a wide variety of inferential goals one has when analyzing these data. So sometimes people just want to sort of take the data and describe the main patterns in the data. Okay, just look at the main features. So that's description. Other times they want to do estimation. So they want to relate some measurements between objects to some predictor information. They want to estimate the relationship between those two sets. So there's estimation. And a lot of times there's prediction. So a lot of times you have some relational data set here, and then maybe you don't get to observe the value of the relationship between some pairs of nodes. And in which case you might want to predict what these missing values are based on your observed data. Okay, so my way of doing things is to build a statistical model of the data, and this allows me to do all these tasks. The model can do both, or it can do description, it can do estimation of parameters, and it can also provide predictions. So that's sort of why I like the model-based framework. So for example, often what we do when starting out with the task of modeling the relationship between some outcome variable and some predictor X, you start with some sort of basic regression model. Okay, so here Yij might be some relationship between pairs of countries. So Yij could be the trade between countries, the amount of trade in log dollars, or it could be the indicator of a dispute between I and J. And here are other variables you might want to relate to that. Okay. So you might start off say, okay, well, what's the relationship? Let's just find the linear relationship between these variables, or maybe linear on some scale. So a basic generalized linear model does that. It finds this relationship between y and x via these linear regression coefficients beta. So this model, this basic generalized linear model, measures the association via these parameters, tells you how strong that association is and how well you've measured it, as well as it can provide predictions of missing data.
Is beta a matrix?
Beta here would be a vector.
Oh,
So for each pair of objects, you might have a vector of predictor variables.
so the beta is also subscripted by I and J, actually.
No. So the X is pair-specific predictor variables, and then the beta is some unknown parameter to be estimated, vector of parameters.
But it's somehow global to the
Yeah.
whole model.
So for example, there's a theory of the democratic peace, which says that democratic countries don't, fight with each other. So Yij might be the indicator of a dispute, and Xij might include in it. So it's a vector, but it might include.
What I don't understand is
yeah.
X seems to be in boldface.
Yes,
and
X
the
is in
rest
boldface.
seems to be in light.
Which?
So
X is in bold-
X is in boldface and
Right.
the rest is in light face.
Yes.
So
So
beta is boldface also.
I tried to make beta boldface, but it didn't work out as well as I'd hoped.
I see. All right.
So
So
beta is a
X,
vector.
so Xij is really X. Is that the ijth element of something, or is it?
Yes.
But it's also a vector itself.
Yes.
Xij is a
Right.
vector.
Okay.
So I guess what's confusing is
Yeah,
what
yeah.
this matrix
Right,
relates to the
right,
matrix.
right. Okay. So this X is really an array of a three-dimensional array.
I see.
Exactly.
It has depth.
Right. So X1, 2 are predictor variables for the pair 1, 2, but it might be several variables long.
And so that's an inner product between beta and X?
That's right.
Right.
Okay. So this type of model is easy to fit. You can fit this type of model with any sort of statistical package. You can do variations on this model, doing logistic, probit regression if you have 0, 1 data, other kinds of models if your data on some other scale. But common to these basic methods of analysis is the assumption that the relationship is additive here, and that deviations from this model are patternless. Okay,
Are
so
what?
patternless. In one way to describe this is to say that these error terms are independent and identically distributed. Okay, they come from some noise distribution. Okay, so that's how these models are usually fit. And so this is certainly wrong. I'll try to convince you why that it is wrong. And well, okay, so here's a network of friendship ties amongst a bunch of children in a neighborhood, and they have numbers indicating their grade. And so what do we see here? We see there's some children who, here this is a directed network, and this child has no outgoing ties. Okay? Whereas, so he says, nobody's my friend. Right?
Why are you looking at me?
Well, two people say that this guy is their friend, so it's not you.
Okay.
All right. So, but there's some other nodes that have many outgoing ties, right? So suppose a new child enters the neighborhood. It seems, based on these data, you might imagine it's less likely that this person is going to go up and be their friend than somebody who's more outgoing. Okay. So this is another way of saying that the
What is the meaning of the distances?
there's little meaning. This was just a way to lay out the data in such a way that things that are close together also have links. But what I just described to you was a way of saying that these errors are not independent. Okay, so some nodes are more outgoing, and this affects the entire row, their entire row. And some nodes are more popular, and that's going to affect their entire column. Okay, so it seems that that this sort of, assuming that this is patternless and the errors are independent, identically distributed, is not going to capture a lot of the features we see in this type of data. Okay, so what's the next step we could do to sort of improve the model fitting? Well, if you're in statistics, the first thing you would be told to try is to put in additive row and column effects. Okay, this is saying that there's a sender-specific intercept, a receiver-specific intercept, and so on. Okay, so you fit a model that relates the outcome to your predictor variables, and then some sort of outgoingness of node I and the popularity of node J, and so on. And then you'd have patternless noise left over. Okay? So if you do this to a network data set, you invariably improve the fit, the predictive performance, by just about any measure you can think of. And to some extent, it also provides accurate standard errors here, as long as they're based on just correlations and covariances, second-order moments. But all this does is represent heterogeneity amongst the nodes in terms of their sort of additive row effect and additive column effect. And it doesn't capture a lot of things that we see in social networks. So what are some other types of patterns that we see in social networks? Well, if you looked at this long enough, you start to see that there's lots of these triangles that you see here. Okay, you see triangles in this network. In fact, you see a lot more triangles than you'd predict, if you just use this model. Okay, and what's going on? What's going on here is that, well, so this is a friendship network, and there's sort of an old saying, a friend of a friend is a friend. And that's actually exhibited here in these data. So what you see are that if person I is friends with J and J is friends with K, then you're more often than not going to see a link between I and K. Okay? And that mathematically is described as it's a third order dependence. Okay? It's it can be represented by this thing having a third order moment, okay? And so just putting in row and column effects affects the second order moments or correlations. And so you can't represent third order dependence with this kind of model. Okay. So all this is building up to the idea that we have to come up with something slightly more complicated than this to describe variability in relational data sets. Okay, so I'm going to have sort of two motivations of a model, and they're kind of different, but they suggest the same thing. And I think one of them you'll be very familiar with, and this first motivation maybe less so. So this is a really cool theorem in probability, and basically the idea is as follows. So in what we saw before, we're fitting a model in, we have these predictor variables x, and that's supposed to describe our current information about the nodes. Okay, so like I said, we might have data on countries, and the x's might be the trade between the countries, maybe the types of government they are, and so on. And then E was supposed to represent deviations from this regression model. Okay? Now we just talked about how we didn't want to treat that matrix E as patternless noise, right? We said there are certain things common to rows and certain things common to columns. Okay? So, however, we don't have any a priori information distinguishing the nodes except for this x. So if we want to come up with a sort of a noise distribution for these E's, it should probably satisfy this cryptically written down condition, which says that the distribution of the EIJs should be invariant under permutations of the row labels and the column labels. Okay? So if I were to say the matrix of residuals is completely patternless, so if I have epsilon 1, E11, E12, E1, 2, E2, 3. So if I could interchange any pair of E's, and that gives me the same probability, then that is essentially saying that the E's are patternless. Okay? Now what we're saying is we shouldn't allow that, right? Because there's something in common to observations in an entire row. Okay? But we don't have any information distinguishing this row from this row. So we should be able to at least switch rows and switch columns. Okay? So that's the basic idea. So we want to have a bit more of a restriction than just complete independence. We want to allow for the possibility that they're interchangeable amongst rows. So this is a type of invariance called exchangeability, and it's called weak exchangeability for arrays. And okay, so use the word a little bit more. So one model, the independence model, says that so the independence model, the assumption that they're all patternless, says that I could just write the probability of my matrix as just a product. Okay. Okay. So there's a probability model for E, and if I assume that all the errors were all completely independent and exchangeable, then I could write it like this: the probability model for that. So this says if I say that not everything is exchangeable, but just the rows and the columns are exchangeable, then that model is equivalent to this following formulation. That model can be represented as follows: that every EIJ can be expressed as some function of a row effect, a column effect, and then patternless noise. Okay? So let me just restate what I just said. So if we have a model such that this is true, that this exchangeability condition holds, which seems reasonable given what we know, then that probability model can be expressed this way. Okay, so if we assume at the minimum that we can do exchangeability between rows and exchangeability between columns, then we can just write our model as a random effects model in which we have effects for each row and effects for each column. Okay, so that motivates this idea of a factor model or a random effects model.
There's no restriction on the form of that, right?
There's no restriction, that's right. That's correct for this one, yeah. There's an analogous representation theorem if the matrix is symmetric. in which case it would be mu, ui, uj, epsilon ij, and we have to have symmetry in the second and third arguments. But, yeah. Okay.
Excuse me, what is mu?
It's sort of like a mean.
Because you say that it's random variable.
Yeah, he's a baby.
Yeah.
It's
The variability in the array is expressed with these things. All right. But this doesn't tell us what this function should be, right? So it doesn't say anything about what this function is. So now I'm going to appeal to another representation here, a very sort of different one. So what's another way to think about this? So E, remember, is our matrix that represents deviations of our data from the model, okay? And what I want to do is sort of decompose this to a part that is patternless noise, and a part that's not patternless noise, that's somehow systematic. Okay. Now, as we know from matrix algebra, every matrix M has a decomposition or a representation of the singular value decomposition. So every such M can be expressed as the matrix product of U, a diagonal matrix of singular values D, and another orthogonal matrix V. And the main point here is that basically the ijth entry of this matrix M can be expressed as the matrix, or the inner product, the weighted inner product of a row effect and a column effect. Okay? So all we've done is gone from this situation where we've assumed a very simple form, additive row and column effects, and to generalize that, we just say that they're multiplicative. Okay? But the neat thing is that we know two things, that every such matrix has this representation. Okay? If it's a complicated matrix, we might need high-dimensional U and V's. If it's a simple pattern, we could only use low-dimensional ones. But we know that this representation is very flexible. Any matrix M can be represented this way. And we also know that any statistical model for these deviations from the regression part can be expressed as sort of this random effects model. So hopefully this provides some sort of justification of this sort of model. So I'll skip.
Sorry, excuse me?
Yeah.
So if we want to take a real probabilistic interpretation of this, should we take D to be playing the role of mu? The diagonal matrix. In other words, you would sample it from some distribution over diagonal matrices.
It's part of it's part of that. I wouldn't say it's part of mu. I would say it's part of the F, because D controls the sort of scale. So if I increase D, sorry, where am I going? Okay. If I increase D, this increases sort of the scale. Okay. And I would think that that's more the F. That would be captured in the F.
Well, then you have a model where you can't learn D.
Well, but if you learn U and V, well, you have to learn F too, right?
I mean, we're just talking about the deviations E, not the basic information.
Yeah. Okay, I'm not quite following, but
Let me ask you a different
But,
question.
the perspective that I'm coming from is,
Yeah.
so Brian and Jordan make a critique of SVD type models on the grounds that they're not generative. And I thought that you were trying to be more generative in this talk. So all I'm trying to do is line those things up.
not generative. I've heard David talk about that term, but I've never quite figured out what he meant by it.
Okay, well, we'll take it.
Okay, let me ask you a different question. Your next slide, did it just tell us that this F need not be any more complicated than second order?
Not quite, but almost.
I don't think so. No.
It says that big E could be your EIJs,
Right.
epsilon IJs, and then you need to add to it something that's a function of mu, UI, and EJ.
Right.
And it looks like if you add that,
Okay. I'm gonna add something that's I'm going to get to the F part in just a second.
Okay.
All right. It's generative in the following sense. Okay, so so I can estimate the magnitude. I can estimate D, okay, based on some data, and I have a model for mu and V, and I'll have a model for that F. I can estimate that F, okay, and then I can sample U's and V's, and that will generate new relational data sets. So it can generate data. It can generate the kind of data that you observe. And in a second, I'll generate missing data based on observed data. So we'll see if that satisfies the definition or not. But okay. So the data analysis based on singular value decomposition has a pretty long history. It's intimately related to sort of image processing, data reduction, in social sciences and psychometrics. It's related to factor analysis. I won't go too much into it. But here's the basic sort of model that we're going to be using. So we're going to have our basic relationship between known covariates or predictor variables x, mediated by some parameter we're going to estimate beta. Okay? And then we're going to have basically a random effects component, which is comprised of these latent factors. Okay, so we're going to actually estimate these U's and V's for each row and column. We're also going to estimate this D, which is global to the system, and then we have some noise. Okay, and so this sort of has a nice interpretation, I think. So basically, you think of these U's and V's as vectors of latent nodal attributes, and then basically the relationship between a pair of objects is related to their vector product of these vectors here. So, so for example, you can imagine that nodes might favorably interact with others that have similar characteristics, but you don't get to observe those characteristics. And so this would capture that sort of behavior. Okay. Now, one of the nice things about a model-based approach is that you can accommodate all sorts of features of the data, such as data that's binary. So this predictor here is on the real line, and so but your data might be binary data, it might be count data 0, 1, 2, 3, and so on. So in a modeling framework, you can accommodate different scales of the data, and here's a simple way to do it. Basically, you embed these things into generalized linear models. And so, for example, you would model the log odds of a relationship between I and j based on this thing here. So I think to go back to the previous questions about this f function, I have been recently instead modeling that sort of non-parametrically. So let's see how I want to talk about it. Basically, the approach is that you have a latent variable zij, which you set equal to this predictor part. And then if you have binary data, then you'd say that yij is 1 if zij is greater than 0, and 0 if zij is less than 0, right? So that would be a model for binary data. Okay? But in general, if your data are ordinal, or they're ordered in some way, right, then, for example, if you have categorical data, ordered categorical data, you could say yij is 0 if zij is less than, some parameter gamma 0, 1 if zij is between gamma 1 and gamma 0, and so on. So you can actually model the sort of marginal distribution of the y's non-parametrically. And this is essentially modeling that f function. Okay. All right, so that's the basic idea. Now I want to go through some examples to sort of talk about how to interpret this stuff and how to use it. Okay, so I know some political scientists at the University of Washington, Mike Ward and Sean Cowan, they gather a lot of data on international relations, and they would like to test various theories of what variables are related to such things as trade and conflict and so on. So they've gathered data on militarized disputes and the direction of the dispute, who initiated it, although that's often a contentious issue. And they want to relate this to a bunch of covariates. So basically the population of the initiator and the target, polity score of initiator and target. And polity is sort of a measure of, it's a measure on the type of government. So it's a measure of how easy it is for individuals to access the government. And so a positive polity score says that it's possible for somebody to enter into government. A negative one says it's not. And then their interaction. Okay, so this is sort of getting at the idea of that democratic peace idea that countries with similar polity scores might not conflict so much. A distance between countries and number of shared intergovernmental organizations. So there's some theory that somehow intergovernmental organizations might actually act to reduce conflict, right? Okay. Okay, so here are parameter estimates. So I fit the latent factor model with 2 dimensions to the factors, and I'll show those estimated factors in just a second. But to some extent of interest to the political scientists was this output, which are basically point estimates and confidence intervals for the covariate information. And so you see that many of the relationships are quite weak. Okay, so this is 0, and so here are sort of the confidence intervals for the parameters, and many of these overlap 0. And what do we see? We see a negative relationship between distance and conflict. So that's saying as distance increases, you're not likely to conflict with each other. And population seems to be positively related to conflict. And so actually the real story here is that often the zeros are driving what's going on. So there's very few conflicts. So it looks like big countries that are, let's see, big countries that have small distances between them are having conflicts.
And the bigger countries are attacking the smaller.
Yeah. So that's one interpretation. But what's apparently really going on is that small countries that are really far apart, they don't go to war with each other, right? Because
Oh, that's what you meant by the zeros are driving this?
Yeah.
I see.
yeah.
Because they don't have airplanes.
Right. It's really expensive for one small country on one side of the globe to go to war with another small country on the other side of the globe. So that doesn't happen. Okay. So I tried to come up with different ways of plotting the latent factors, and here's one of those ways. And my political science colleague called this the ring of fire. And so remember, in this model, it's directional data. And so every country has a vector of attributes as an initiator of the action and as a target of the action, right? And so what I've plotted
And each
here...
vector is 7 dimensions.
Pardon me?
Each vector is
2 dimensions.
2 dimensions.
Yeah. So what I've plotted here are the directions of each country's initiator vector and each country's target vector. Okay. And so this was 1990 to 2000, and so over here, so basically what's going on is the First Gulf War, and so here you have Iraq and other countries with their targets. So these are actually coded events. So it's not like they just said, oh, there's this war and that's one event. They're actually looking at all the different sort of attacks and things like that. So here you have Iraq, and then somewhere embedded here you have the United States, and then down here you have the United States initiator vector, and then Iraq is in there. Okay, and then over here you have conflicts that are going on in Africa at the same time, which are more or less unrelated to this conflict, right?
And the font size?
The font size is the magnitude, related to the magnitude of the vector. So I have to come up with some way of doing that, because if you just plot the actual vector with the length of the vector, it looks like a mess. So And then the green lines are the actual conflicts between the countries. And so to some extent, we know that the structure, the residual structure after having the x's in there, is capturing something. If it weren't, then we wouldn't be able, so notice something about this figure is that there's very few lines that go across the center, right? So if the residual structure was not able to be represented with 2 dimensions, then we wouldn't be able to come up with such a configuration. So that's representing the leftover structure. So what time is it?
No, 20 more
20 minutes. Okay, I'll skip this slide then. But there's a similar slide coming up, so not much is lost. Okay, so just a quick note on undirected data. So a lot of times we have that we have a symmetric matrix. In other words, Yij equals Yji by design, right? So friendship network, well, some friendship networks. So previously I talked about a protein-protein interaction network, which is indicating whether proteins will bind. So that's undirected. And so there's a similar symmetry argument that says that you should model such data with node-specific effects, and whatever function you use to link those node-specific effects to the outcome needs to be symmetric in the second and third argument. So that's sort of obvious, and then the matrix analog of that is, of course, the eigenvalue decomposition. Okay. And I guess I should point out that you can't get these things just by actually doing the eigenvalue decomposition. In particular, for example, in interaction data, you don't actually have a diagonal. Okay, so you have to be a little bit more tricky with the estimation. But in any case, for symmetric data, we have this analogous model. So we have our latent factors involve a product of the effects for node I and j, and then weighted according to the eigenvalues. And an example of that is the following analysis. So here's a very often used data set in looking at models of this sort. So it's this big, it's not that big, I guess. It's 270 by 270 symmetric matrix, mostly filled with zeros. About 1% of them are ones, indicating link between the proteins. And so then we decided to sort of look at the structure in this matrix. And so there's no predictor information here. We're not including any predictor information. So this was kind of interesting. So again, I've plotted the directions of the latent factors around a circle. Okay? But you'll notice that, as opposed to the previous example, there's lots of lines crossing through the center of the circle. And how are they crossing? It's not completely just all over the place. It seems that the lines cross mostly in a very systematic way. Okay, so remember, not only are we estimating the latent factors for each protein, but we're estimating eigenvalues. So can someone tell me what the sign on the first eigenvalue is? Without looking at the labels on the plot? All right, so what do we see? If we were just to look at this dimension here, what would we see? We'd see that links are occurring between things on the same side of the x-axis, right? So these guys link to things down here, and so on. Okay? But we also see that things are linking to things that are on opposite sides of the y-axis. Okay? So here we have things tend to link if they have common values in their first dimension, that's a positive eigenvalue, and opposite values on the negative direction, so that's the negative eigenvalue. Okay? And a lot of data sets are like this, where you see networks where nodes have roles, and two nodes might have similar roles, but they don't interact with each other. Okay? So that's where this kind of model is reasonably flexible. Okay, and then we can go in and look, and in these sort of groups, you find sort of these proteins that are linked that have specific biological structures.
You're running out of time, but I have a
Yeah.
question.
Yeah.
That last plot didn't suggest that your model's too simple?
Um,
Because previously, you said since there weren't any green going through the middle,
right.
that was a suggestion that the residuals were small in some
Right.
sense. And now this one had a lot of green.
Right. You're always going to get green here, no
Okay.
matter how many dimensions you fit.
Okay.
Just because of that fact that there's a very strong negative eigenvalue in this, for these data.
So for some kinds of problems, that residual analysis wasn't the right analysis that you
Well, so,
informally went through on the first plot.
well, here's the thing. So if I do this type of model, I can absorb the, if I do the sort of SVD model, right? I can make, if there's sort of a negative interaction that way, I can make a country's V the negative sign of their U. I'm gonna have that freedom. But in a symmetric model, I can't do that. So you have to have those eigenvalues in there. Okay. Okay, so what is the use of something like this? So in these types of experiments, it can be really expensive to run experiments on all pairs of things. And you can imagine in a social network, if you're looking at relationships amongst people, it's really hard to go in and like measure the relationship amongst everybody because that's n choose 2, and that's a big number, right? So one thing I've been doing is sort of these sort of prediction experiments. And so what you can do is you can take this matrix of data and you can fill it with holes or missing values. Okay, so maybe you have an undefined diagonal, 1, 0, 0, 1. But then you have things where you don't know if it's a 0 or 1 or not. Right? Okay, so I don't mean fill it with holes in terms of filling it with zeros, I mean filling it with an indicator that you don't have an observation there. And then the goal would be to predict what would happen if you were to run that experiment. Okay? And so here's sort of a version of like an ROC curve or something. So so what I did is I threw out like 1/4 of the data. Okay, I filled this data matrix, filled it up 1/4 with NAs, missing values not available. And then I fit the model. Okay, I can do that because I have information on, I just have to estimate a row effect and a column effect. So as long as I don't throw away an entire row, I can still estimate that row's effect. Okay, and so then once I have a row and a column effect, I can still get a predicted value for each missing cell. Okay, and so then what I did is I had this little sort of thought experiment. So if you were the researcher, you'd want to know what experiments to run next, right? So what you do is you go run the experiment that had the highest predicted probability. You do that one first and see if there was an interaction there. Then you do the second one and so on. So here's a plot that sort of shows that. As you increase the number of pairs checked, how many actual links do you find? So that's what this plot is showing. And what I did here is I fit a one-dimensional model, a two-dimensional model, and a three-dimensional model. And basically, so this is showing that this is a way to sort of figure out how many dimensions you need to achieve sort of good predictive performance. So here's that. Okay, so I think I just have barely enough time to talk about extensions to multi-way data. And here's an interesting idea that it wasn't me who came up with it. It's a bunch of people in Scandinavian countries, as far as I can tell, and it hasn't really left there yet. But so a lot of these data are actually derived from data that are not sort of data on pairs. They're data on more complicated structures. So for example, I've seen social networks where the social network is, people have many different sources of information. And they'll see in each one of their sources, is there a link between nodes I and J? Okay? And so really, what you have, or another example is you have text documents, and you're looking for sort of co-occurrence of words. And so you have a sociomatrix or a matrix representing links between words in one document, you have them in a second document, in a third document, and so on. Okay? So for each document, you have a different bit of information there. And so what you really have, you don't want to just compress this down because that's ignoring variability across the documents. Okay? So what we want to do is accommodate not only variation in the rows, not only variation in columns, but also variation along this third dimension. Okay, so how might we do that? Right, so here are some other examples of that sort of thing. So with the international relations data, people often measure relations across time. So you might imagine here we have a conflict network, in 1950, 1955, 1960, and so on. Okay. So, well, let's see how we might extend the factor model in 2 dimensions to multi-dimensional data. So in our factor model, we model the systematic part as the product of these vectors here. If we're doing that with a rank R matrix, that's just saying, or dimension R vectors, that's just saying that this is equal to UIR, the sum over R of UIR, B, JR, and then weighted by the singular value DR. Well, what's the extension to 3-way data? Well, suppose we have 3-way matrix and our entries are IJK, so we just say the sum over R, UIR, BJR, WKR. So we just add in a factor, right? So now we have the vectors U representing variation along one dimension, V along the column dimension, and then W along the third dimension. So it's the direct analog of that. And in fact, there's a lot of theory which talks about how this generalizes the notion of rank for multi-array matrices. But for our purposes, it provides a way to think about representing variation along more dimensions. Okay, and yeah. So how much time do I have? 10? Oh, okay. All right. So I'm going to show you a quick example of this, and I'm going to try to interpret it, but I finished the data analysis, I think it was like Sunday night, so we'll see. Okay. So how might we interpret this kind of model? Well, we can actually interpret it in a similar way to the singular value decomposition model we had before. So let's think about, so here you have essentially slabs going along this third dimension. And let's think about the kth slab here. That's slab K. Okay, slab K is a matrix itself, right? So K is fixed, and then we vary I and J. Okay? And so in the K slab, entries in the K slab are given by this form right here, U, I, R, V, J, R, W, K, R, and D. But across this slab, the values of W, K, K doesn't change. So I can just combine W, K, and D here. I get a new thing called DKR. And this is just the same form as we had before. So this is just saying we just have a singular value decomposition across each slab where the row and the column effects remain constant across slabs, but the singular values are changing. Okay. So what's the interpretation? Basically, let's see, what is the interpretation? So basically each node has a bunch of sort of latent factors, and in different slabs, those the dimensions of those factors have differing sort of importances, right? So in some slabs, some dimensions are more important than others, okay? So here I'm going to try to give an example. Okay, so here's a different conflict data set. Actually, it's not just conflict, it's also cooperation, which is good, right? So it's actually cooperation and conflict from 1950 to 1985. And I did it. Yeah.
But each slab has the same latent factors.
Right.
Just
So
with different.
the variation across slabs is completely represented by variation in the singular values and not the factors of the row and columns. Here, I'll skip to this plot, and then we'll go through it. So this is kind of a mess. I apologize. It needs a little bit of touching up. So I had data every 5 years from 1950 to 1985, and so let's just focus on this top row for now. Okay, let's just focus on the top row, because I did it in 3 dimensions, and because I thought, you know, I'll try to be more bold than just doing 2 dimensions for once.
And you regret it now.
Yeah. So let's just focus on this. So U1 and U2, those are the dimensions of each country's latent, first and second dimension of each country's latent factor. So you can see here in 1950, 1960, US is in the same place, UK, Israel, right? So there's some countries that don't, not all countries appear in every single plot. So I've only plotted the ones that are actually having cooperation, alliances, or conflicts in these years. But the point is that the positions are staying the same, okay, for the countries, but we do see changes in the patterns. Okay, so just to make it brief, here we see in 1950, okay, we see a lot of stuff going on in this U1 dimension, okay? So that seems to be the most important dimension in 1950. And actually, it fit a 3rd dimension, and that's not a lot of stuff is going across that 3rd dimension. But what's going on here? Here we have the United States, Republic of Korea. Here we have China, People's Republic of Korea. So this is the Korean War, right here. We also see a lot of stuff going along that direction in 1970, and here in China we have Vietnam. Okay, this is the Vietnam War. Okay, this dimension you can sort of interpret as basically conflict in Asia. Okay, whereas if you sort of pour over these things and all the other years that I didn't plot, the 2nd dimension is more of an east-west block sort of thing going on in Europe. But what this sort of multi-way model does, so here are the eigenvalue, or the singular values, and remember we said variation across years is represented by variation in the singular values across years. So in 1950, so in 1970 we see very similar patterns. They have high values of the first singular value and small values of the second and small values of the third. So most of the stuff is going along that direction. In both 1950 and 1970, it's most of the stuff that's going on is conflict in Asia. Okay, and then you can also get regression coefficients and so on. Okay, so I think I'll end there. So the point of this talk is that latent factor models it's a natural, simple way to represent variation in array type data, not just matrix data, but also in higher dimensions. It can be incorporated into a variety of model forms. So there's model-based ways to do this sort of model-based decomposition, even if you have data which are binary or count data and things like that. And so with these model-based methods, you can get parameter estimates, accommodate missing data, make predictions, and so on. Okay, so I think I'll end there. Thanks very much. Yeah.
In the missing data case, do you need to use sampling to do estimation?
You need to do sampling. What do you mean?
I haven't thought through this.
Okay,
it's
sure.
not a question, but
I'll want me to tell you what I do to.
sure, that's
okay.
easier.
All right. So I didn't talk at all about how I estimate parameters here, did I? Okay. So I use something called Gibbs sampler, which gives.
What I said.
Okay. Okay. There we go. Okay. So basically, I generally use an approach called Bayesian parameter estimation, in which I obtain a probability distribution for all unknown quantities in the model. Okay. And I actually can obtain samples from these posterior distributions. So for example, in the matrix I just erased, I have So in the Bayesian framework, everything that you don't observe, you can get a posterior distribution for. So you have a probability distribution for everything that you don't know. Okay? And so for example, I don't know what's in here. And I can get samples from the posterior distribution of this entry. And so sometimes I'll get a 1, sometimes I'll get a 0, but maybe 80% of the time I get a 1. And so my posterior probability that this is a 1 is 80%. Okay? And the reason you can do that is because that probability is related to my UI, VJ vectors, and these I can estimate based on the available data. So as long as I have some information on each row and some information on each column, I can make predictions about missing cells.
I have a clarification question. When you went to the three-dimensional data, I, J, and K, you chose to sort of think of the slabs for each K.
Yeah.
But otherwise, the statement is quite symmetric, right? Like
Yes,
sort of
that's
child
definitely
K.
correct. Yeah.
Right.
So the types of data that I've worked with are typically where you have basically a social network, maybe measured over time or measured on different variables. So for example, what I want to do is basically get away from the idea that somehow trait is a predictor variable and conflict is an outcome variable. I'd like to model them both as being, coming from some model. And so I could have, one slab being trait, one slab being, conflict and so on. And in those cases, I have row and column effects being constant across the thing, and then I have this dimension, this other dimension. But you're right, you could have, one thing could be nouns, one could be verbs, another could be documents or something like that, right? And so you could talk about slabs in any dimension, any two dimensions.
Is there, I guess this is more a clarification question, is there an appropriate interpretation? Because, when I think SVD for two-dimensional things, it's sort of an L2 fit of the lowest rank or
Right.
whatever. Is there a corresponding interpretation as this the lowest rank?
Right. So
I don't
actually,
even know what to think
right.
of rank
Okay.
right now, but
So let me clarify that a little bit. So, so I've kind of confused a couple of things here because I called it the SVD model, but I didn't actually use the singular value decomposition to obtain the parameters. So, so we have a computational procedure that can obtain this SVD for any matrix. We don't have the same thing in higher dimensions. But fortunately, I didn't use the singular value decomposition to obtain things. So, so you can obtain parameter estimates in a similar way in the higher dimensions as I did here in two dimensions. But I don't. There's no good. The theory in higher dimensions is for matrix decomposition is really not very informative, I'll say.
and the WKs, WKRs are also orthogonal in some way, the way you do it.
Yeah. There's some really interesting stuff there, though.
Okay.
So whereas some things are invariant in the two-dimensional case, they're not invariant in the three-dimensional and higher case. But it's kind of a mess. Yeah.
Could you put on that picture of those red lines, conflicts 1950
Yeah.
through 85 or whatever?
Yeah.
Okay. Okay. What places a country in a particular position?
Oh, so these are so each country has a vector. I should point out that this data was actually, it was decided that we couldn't decide who initiated any conflict. So we just looked at whether two countries were involved in a conflict or not. And so that, sorry, let me back up a little bit. Yij in this situation was -1 if I and j are in conflict. Yij is +1 if they're in an alliance and 0 otherwise. Okay, and then we related this to, we modeled this Yij as a function of Ui transpose Uj with some weights given by these eigenvalues here. And so what these locations correspond to are these actual vectors here.
And you estimated those
I estimated those.
in 2 or 3 dimension,
Yes.
and the matrix changed for each year, but
Right.
the estimates did not
Exactly.
change.
Right. And so what happens is that, for example, United States and the United Kingdom throughout this period are generally in alliance in every year.
So alliance means no red line.
Alliance means a green line. Sorry, I should have made that clear.
But there is, I see it now, yeah.
Yeah.
I didn't see that, all right.
Right. So what you get is that basically Western European countries are generally over here, and they're in alliance together when there's a conflict in other places. And right. So I mean, you think about it, the eigenvalues in 1950 were positive for this thing, and so basically 2 countries that had similar vectors, they have a big positive outcome, and so they're in alliance. And if they're on opposite sides, the inner product of the vectors is very negative, and that gives them a minus.
But what I don't understand, I don't know about your mathematics, but what I don't understand is, except for the Soviet Union, you're missing all Eastern nations.
Well,
I don't see any
only
Poland.
plotted-
I don't see any Poland there,
Right.
any Albania, any nothing.
Right. I didn't plot any countries that didn't have a conflict in that year.
But they surely had an alliance.
Yes and no. So these were very specific types of alliances, basically cooperation, military cooperation, in an actual event, not just something on paper that said that they would actually.
So just being in NATO is not enough?
Exactly.
Okay.
Right. So you have like troops together. or
You
something
could
like
have Poland actually going into Hungary.
So in other words,
Yeah.
Or something like that.
the idea would be that, like, for example, the current war that's going on, you would consider a green line between US, UK, Spain, Poland, whoever contributed troops.
I think so.
And,
Yeah.
and so even though they don't have any formal alliance between
Right.
them, the fact that the
But
US
you
and
wouldn't include everybody in NATO. for
Exactly, because they weren't actually involved in this.
Right. And if you look at the 1950 data more close up, it's kind of interesting because I learned something about Yugoslavia, and it was, what was it? That they were kind of against the rest of the Eastern Bloc or something, and they're sort of in a different part than the rest. So
Basically,
Marshal Tito's
Tito,
still-
Nehru, and somebody
Yeah.
formed this non-aligned movement.
yeah, that's exactly what it was. So I actually got to learn something. So,
Well, actually, the 3D plot is also informative because in the 2D plot top left, US is on the bottom left, USSR is on the top right.
yeah.
But when you turn the cube around, US is actually, if you look at the top picture, much in front of USSR.
Yeah, right. So this is, if you imagine all this in a cube, this is the sort of front view, the top view, and the side view maybe.
And the moral
Well,
is
the
never,
big-
never try to do more than 2 dimensions.
Never do more than 2 dimensions.
So in the other plots, the location of the vector means something in a vacuum. Just the US's vector alone.
Yeah.
So one interesting thing about this data set is you have 3 variables, oh no, wait a minute. No, hang on.
No.
These are the 3 linking factors.
Yeah, okay. What I wanted to ask about was about changes over time. So there's something interesting going on here, but now I'm.
Oh, yeah.
Yeah.
Well, right. So
Yeah, what you're plotting here is latent variables. What you actually, sorry, this is remind me what goes into the model. You've
sure,
got it.
right. So this particular model that I used here said that each country has sort of a latent variable that doesn't change over time. Okay. So in a lot of situations, you would want to have a model where things change, like latent variables change over time, but here they don't. Okay. And so what happens is the United States has, over this time period, the interpretation to some extent, the United States has some position in this direction, shall we say, in terms of East Asian politics. Okay? And China has a different position. Okay? And that's constant through all the years. But then in terms of what we observe from year to year, are different sort of weights on those dimensions. So in some years, there's a lot of conflict in East Asia, and so that year will have a high weight on that dimension. So in particular, in 1950 and 1970. Yeah. So that's what we have there. And then, so basically,
No, okay, sorry, I recovered my question.
okay.
Okay. So your three variables here are whose country A, which is categorical, whose country B, which is categorical, and what year is it, which is integral.
Yeah.
And there might be sort of a general question. There are two questions really. One is, might you want to do some smoothing across the interval variables or parametric modeling?
Yeah.
And the other is raised by what you asked, whether things might, whether you might have some properties that change over time, and
Right.
what the best way is of getting that in the model. And I can sort of imagine a couple of ways of doing it, and I'm not sure which the best one is yet.
Yeah, I mean, I think it does depend on the application. So, I mean, I think actually this temporal data set is not a particularly good choice. It happened to be the data I had at hand to present this method. But so you can imagine if you had, you know, word associations in a bunch of different documents. There's no ordering to the documents, right? And so you want to represent variation across words and also documents. And I think this type
Sure,
of
then this
approach-
model is great.
Right. In this situation, if you had, I think for these data it maybe works out okay, but if in general, if you had something that was not varying very rapidly over time, was sort of smooth over time, then you'd want to maybe use this model and make some sort of correlation of the weights over time, would be one possibility. But if you really believe that sort of countries were moving into different directions and, you know, into semi-permanent different directions, then you'd want to use the latent vectors to change over time. So I think that would be a very appropriate model in many situations. Now, the only caveat is that in that situation, you'd have to estimate a latent vector for every country at every time point. Okay, so that's a lot of parameters. I'm not saying that it shouldn't be done, but here's a much more
But you
parsimonious.
could assume that there was a linear trajectory or something, and then it's much cheaper.
Yeah, yeah. So I mean, those are two different models, and I think they would be appropriate in different circumstances. Yeah.
Thank you.